In this section, we discuss absorption in more detail so we can understand the materials engineering for optical devices, such as solar cells. Photon absorption requires that the light intensity must decrease as it passes through the material. The likelihood that a photon will excite an electron and hole pair depends on the concentration of photons, which is determined by the light intensity. The likelihood of excitation also depends on the photon finding appropriate electrons to excite and available electron states to excite into, which means the absorption probability increases as the light passes through more material. This means that the decrease in light intensity, delta I, will depend on the intensity of light I, how much the material it has crossed, delta X, and a material property alpha that encompasses the probability a given photon will be absorbed per a given amount of material. The negative sign indicates that the intensity decreases as the light passes through the material. The solution to this differential equation is a simple exponential decay, where the light intensity at x equals 0 is the incident light intensity that then decreases as an exponential as it is absorbed by the material. The absorption coefficient alpha describes the rate of decay with units of 1 over length. When the absorbing material is much thinner than 1 over alpha, the intensity of light decreases proportional to the thickness. But for thick materials, the exponential form needs to be used. Absorption can occur for a photon with energy greater than the band gap, as long as there are available electrons and empty states at the right energy. This leads to the generation of an electron in a conduction band and a hole in the valence band that might have energy greater than the band edge states. The excess energy of the electron or hole produced is quickly dissipated by a process known as thermalization, where the electron in the conduction band quickly drifts down to the conduction band minimum and the hole floats up to the valence band maximum. Thermalization is typically much faster than recombination, so that we usually think of the excited electrons and holes as being in the states near the band edge, as we do in a heavily doped semiconductor. The absorption coefficient as a function of photon energy for silicon and gallium arsenide are shown on the right. The absorption is essentially 0 until the photon energy has energy of the band gap. For silicon, that is 1.1 electron volts, while for gallium arsenide, it's 1.4 eV. At exactly the band gap energy, the absorption is not very strong because there are relatively few electron states at the band edges. Recall that the density of electron states for a semiconductor band can be described by a square root of energy function that rises from 0 at the band edge for both the conduction band with increasing energy and the valence band with decreasing energy. Thus, a photon with slightly higher energy than the band gap will have both more electrons available to excite in the valence band and more place to put the electron in the conduction band. So the absorption coefficient rises quickly above the band gap energy. The absorption coefficient for silicon rises several orders of magnitude more slowly than gallium arsenide because silicon is an indirect band gap semiconductor, while gallium arsenide has a direct band gap. At much higher photon energies, silicon can have direct transitions and the absorption coefficient becomes as high for silicon as for gallium arsenide. Recall that when discussing the continuity equation for charge carriers, we expected the photogeneration rate of electron and hole pairs to depend on the light intensity. We can use the continuity equation for photons to find the relation. The continuity equation for photons would concern the density of photons, n photon, which would be the number of photons per volume. The rate this photon density would change with time would depend on the gradient of the photon flux. The light intensity I is the energy flux. To convert to photon flux, we divide by the energy per photon, hf. Then we need a photon sink term, which we will call g photon, to account for the absorption rate of photons to make electron-hole pairs. From the steady state condition, we can get g photon from the gradient of the light intensity. We know the light intensity decays exponentially with absorption coefficient, so the gradient of I is simply minus alpha times I. Recognizing that the electron-hole pair generation rate should be equal to the photon absorption rate if every photon absorbed creates an electron-hole pair, or at least proportional to it after including a quantum efficiency factor, which describes the fraction of photons absorbed that actually make electron-hole pairs. Thus, we have shown the generation rate of electron-hole pairs is indeed proportional to the light intensity, but also proportional to the light absorption coefficient, alpha.